Hello, Algebra 2. It's a CFR1 Practice 1. I'm going to kind of go over a couple. I forgot the pen again. Okay. Okay, let's do this again. Hey, okay, Algebra 2, CFR1, Practice 1. What we're going to do this first page is more of kind of a review, and then the next two pages are really what we're trying to get into for your 1 and 2 type level. Domain range and end behavior, that part is the 1 and 2 level, and the 3 level is being able to graph a linear function on a limited domain. And that's not in this practice, but that will be in the CFR1, CFR2, Practice 2. So let's go and take, it's also in the guided notes for CFR1. So let's go ahead and take a look at this. This first part says, are the following relations of function y or y not? And this takes you back, this part takes you all the way back to Algebra 1, okay? So what we're trying to get at is, does each input have exactly one output? Right, that's what defines a function. The function is defined as each input has exactly one output. These are called mapping diagrams. And if I'm looking at a mapping diagram, this is my input and this is my output. I don't need that, it's not a zero. This is my output, right? Each input has exactly one arrow going from it or one line going from it. So this makes this a function. Yes, this is a function. Yes, function. Or let's go function. Let's write function here. With the reason being that each input has exactly one output. Has exactly one output. Okay. So each input has exactly one output. Okay. Not more than one. Now let's look at B. Let's look at B. So these are, again, my inputs and my outputs. These inputs have, well, if I'm looking through here, this has got 1, 1, 1, 1. Hey, whoa, this has got 2. This has 2 outputs. This is not a function. And the reason being is not every input has exactly one outputs, or input 9, an input of 9 has 2 outputs. The input of 9 has 2 outputs. That means that cannot be a function. Now, some of you might be looking at this part here. There's 2 values going to 1, or there's 2 arrows going to 1 in the outputs, but that's okay. That's okay, because each input was only having 1 output until we got to 9. Okay, so that's what you're looking for in a mapping diagram. Now, this will convey the same thing. We had some kind of test that we did in here. I was already drawn in, but we'll do it. And this is the graph of the function or relation in this case that we have to try. And what we do is, again, each input only has one output. And in this case, what we do is called a line test, or the vertical line test. What we do is we pass a vertical line through the function or relation that we're testing. And if those vertical lines, if any vertical line you draw can hit more than one output, then it's not a function. So let's go ahead and look at this right here. If I draw this line right here, that line hits 1, 2, 3 times. So this input right over here, it's a little bit less than -1 or more than -1, would have 3 different outputs. So this is not a function. I'm just going to abbreviate, not a function, FN, because it fails the vertical line test. Vertical line test. And so with graphs, it's really nice because you just apply the vertical line test. If you draw that line, draw any vertical line, if it hits more than one time, it's not a function. If it only hits one time, it is a function. Looking at this, look at F right here. There's no vertical line that I can draw that will hit more than one time. So this is a function. And in this case, we're going to say because it passes the vertical line test. Vertical, we'll abbreviate VLT. Okay. All right. Now, you could do the other 4 right there on your own. This right here is getting to the interval part. This is one-dimensional interval kind of stuff going on here. So we're just looking at X values, right? Before we move on to the X and Y. So this is not a part of, this is not the ones that you will be doing for the summative, but you have to understand this concept in order to apply it to the two-dimensional one. So in this case, we're just looking at X's. And when I'm looking at these number lines, I look to see what my smallest value is and my biggest value is. Well, with an arrow pointing left, my smallest value is negative infinity. And my biggest value I have is -2. That dot that's filled in, a filled in point means it can be included in the set. So if I'm going to write this in inequality notation, when I have an infinity, I only have to do one number, which is really cool. So I've got this X value and I've got -2. Do I want things bigger than -2 or less than -2? Well, in this case, I want things at least less than -2, because we want things going to the left. And now we're looking here because these are smaller numbers. Was this filled in? And it sure was. So it could be less than, or it could be equal to -2. And I love doing inequality first because that sets me up really, really well for set notation. I just draw my fancy bracket. X, the set of numbers in X, such that, that's that vertical bar, that's that vertical line, such that X is less than or equal to -2. And then my really bad version of the right bracket. And that's it. That's it. That's all you got to fill in. That's set notation. Interval notation, still near and dear to my heart. It's my favorite. It's my favorite. You take the smallest value and write it down. You take the biggest value and write it down with a comma in between. And then you say to yourself, self, do I know the number for negative infinity? Does it touch negative infinity? No, you don't know the number for negative infinity. It will only ever, infinities will only ever have parentheses with them. That's saying that it doesn't include that n number because we don't know what that number is. In this case, and the right-hand side, because it's filled in, this we put a square bracket on. So this says, once again, all three of these say the same thing. This says that my lowest value is negative infinity, my biggest value is -2, but it also includes -2. Well, what do you do when you've got, in this case, a line segment or a segment, a bounded value? Well, you still do the same thing. You write your smallest value, 0. You write your biggest value, 3. Well, because I've got two values, I'm going to have two different things going on here. So I'm going to say X has to be somewhere between 0 and 3. It's going to need to be at least bigger than 0 and at least less than 3. Because this is open at 0, it's not or equal to, but because this is closed at 3, it could equal 3. So this is saying that X is somewhere between 0 and 3, but it could be 3, but it can't be 0. 0 is less than X, which is less than or equal to 3. And set notation, once again, write this business down. The set of all numbers X such that X falls between 0 and 3, including 3. Oh, wow. Hey, that's not bad. Not a bad bracket. Interval notation, once again, near and dear to my heart, my favorite. What's the smallest number? 0. What's the biggest number? 3. Put a comma between. Can it be equal to 0? No. Parenthesis. Can it be equal to 3? Yes. Bracket. Bracket. Now you got 2 to practice with on your own. Let's go ahead. Let's roll to these things. I'm going to do 2 of these. I'm going to do A and C. So again, we're going to do the same thing, but in this case, instead of having just one dimension, just X, now we have both X and Y. Okay, so let's do this. I've got my small x, I've got my big X, I've got my small y, and I've got my big Y. I like taking care of the domain first, my X values first. So if I look at this going on here, I've got an arrow that's just seemingly pointing out that direction. It's going that way, right? That direction indicates that no matter what I go to, If I put my smallest value, I could keep going all the way that way in X, all the way this way. And I could still have an X value that would give me a Y value. And just like I put in the guided notes, if you see that arrow pointing this way, your smallest X value is negative infinity. Just like if you look at the right-hand side, since that right-hand arrow is pointing out also, the biggest X value is positive infinity. And then here's where the difference is. Here's where the difference is. And Y in this case, I've got no values down here. The first Y value, my smallest Y value, because I'm going from down to up, is 0. Is 0. I think it touches 0 and you might not. We'll talk about that difference in a minute here. The biggest Y value, well, I got arrows pointing up. We're raising the roof, right? Yay. I don't know. We're pointing up. So those values, so what's up? Not much what's up with you. There we go, got that out of the way. Up is positive infinity. So my smallest Y value is 0. My biggest Y value is positive infinity. So inequality notation. Well, this goes from negative infinity to positive infinity. We called that something special because that includes every number going to negative infinity to positive infinity. What's that thing? What happens when you include all the numbers? That is all real numbers. So the beauty of this, I love it when this happens. That's my inequality notation. That means all real numbers. And once again, that's from the guided notes. And in set notation, the set of all numbers in X such that X contains all real numbers. Okay. Now, what I like to do, for interval notation, we have to put these things. You cannot just call it all real numbers. You've got to tell me it goes from negative infinity to positive infinity. And since there's no exact value for those things, we're going to put parentheses on them. Okay. So again, we've just taken care of the X values. Now we need to look at the Y values. We need to look at the low end to the high end. In this case, we only have one number that we know. Yes, it goes to infinity, but we don't know what that number is. So I'm going to, right now, I'm going to have Y, I'm going to say 0. And I want numbers that are bigger than 0, because that's the direction that these go. So if I want at least something greater than 0, I would write that. And in my opinion, I think it touches. So I'm going to put Y is greater than or equal to 0 in this case. So what else am I going to do? So when it comes to set notation, Y such that, or the set of all numbers Y such that Y is greater than or equal to 0. And then interval notation, again, we go from low to high. So the smallest number was 0. The biggest number was positive infinity. I say it touches 0, and we don't know what positive infinity is. Now, you're saying, Mr. Brayman, I don't think it actually touches 0. And to that, I could not argue against you. If you said it doesn't touch 0, that's absolutely fine. What you need to do, however, is this. You need to make sure that all of these agree. You need to make sure all these agree. If you just want Y is greater than 0, then you need to have it represented in set notation, Y such, set of all numbers Y such that Y is greater than 0. And then you need to have it down here from 0 to positive infinity. Notice how all three of these agree. You need to make them agree. If you don't think it touches the value or a value, represent that in all three notations. There we go. End behavior. As X goes to positive infinity, as my X's get bigger and bigger and bigger, my F of X or my Y values go where? In other words, if I draw this to the right, if I'm looking at this, the right-hand side of my equation, where does that point? I know it's behind this. I'll just rewrite this. Where does my right arrow point? If there is an arrow, first see if there's an arrow. We're going to see that in a second. There is an arrow. It's pointing up. So as my X values get bigger and bigger and bigger, where do my Y values go? They go up. And what's up? Done making the joke. Positive infinity. You're basically looking, where is the arrow pointing if there's an arrow? In this case, it's pointing up. Up means positive infinity. Same with the other side. As x goes to negative infinity, the f of x values go to, well, where's the left-hand side pointing? It's pointing up. Up means positive infinity. Okay, so you've seen one example where we do have some end behavior in here. What happens if you get something like, I don't know, how about B? We're going to approach this the same way. And this is the last one I'm going to do. I'm going to make sure the answers are here for you, though. This is the last one I'm going to do. We've got the small x. We got the big X. We've got the small y. We've got the big Y. I will also point out, be very careful what your small y is in for part C. Okay, so what's our small x to big X? The smallest x value I have, oh, this stops right here. This stops at -5. Oh, and this one stops here. This one stops at 4. Okay, so we've got some stuff that doesn't go to infinity. Let's look at our small y value. So again, this was -5 and 4. The lowest value that I have in y is -3. The biggest value that I have in y is 4. So how do we do this then? In inequality notation, you've got your x values, right? My smallest was -5 because I have two values that I know. My biggest was 4. X has to at least be bigger than -5, but at least less than 4. This case on the left with -5, we had an open side or open dot, so it did not include -5. But on the right-hand side, it included 4. So less than or equal to 4. This tells me that my x value is somewhere between -5 and 4. It can't be -5, but it could be 4. Set notation is beautiful. X, the set of all numbers x such that it's between -5 and 4, including 4, but not -5. Interval notation, again, near and dear to my heart. Lowest number, -5. Biggest number, 4. Can it be -5? No. Can it be 4? Yep. Oop, I just screwed that up. Yep. Love it. Absolutely love it. We're going to do the same thing in y. My y value, we do have two values in y that we know also. My smallest value is -3. My biggest value is 4. Y has to be somewhere in between. It's got to at least be bigger than -3 and less than 4. It can't be -3 because that's an open dot, but it could be 4. We're going to make that a closed. There's my inequality notation. And now that I've written my inequality, now I really have what? I've also got set notation. It's a thing of beauty. The set of all numbers y such that y is somewhere between -3 and 4. Well, we'll try this bracket. Not including -3, but including 4. Interval notation, once again, write the small number, -3. Write the big number, 4. Can it be -3? No. Parenthesis, can it be 4? Yes. Bracket. And now onto end behavior. End behavior is literally what happens at the ends. What is happening at the arrows at the end? So as x goes to positive infinity, f of x goes to. So let's look at the arrow. Let's look at the arrow at the end. The arrow. There is no arrow. X doesn't go to positive infinity. Well, since x doesn't go to positive infinity, there's no end behavior, or the end behavior does not exist. DNE. I'm going to put a little note up here. DNE does not exist. This end behavior does not exist. If there's not an arrow, the end behavior doesn't exist going that direction. If I look at the other part of this, going to negative infinity, x doesn't go to negative infinity. So once again, there's no end behavior. So as x goes to negative infinity, f of x does not exist. The end behavior does not exist. All right, I'm going to finish this one out. I'm going to put this video up. I'm going to put the solutions up. Have a great day. We'll talk to you later.